Good day and welcome back to part 4 on our discussion of derivatives as a function. In our previous video, we ended by looking at some examples graphically of given a function. Can we sketch a graph of its derivative? And we started to discuss the idea of what it would take for a function to not be differentiable at a value. And we had a conjecture from our previous example that it might have something to do with a sharp point in the graph of a function. And the simplest example we could consider of a graph that has a sharp point present would be that of the absolute value function. So let's think about this first graphically, and then we'll think about it analytically. For the function f of x equals the absolute value of x, where is the function differentiable? What is its derivative? Graphically, you would most likely describe the absolute value function in terms of maybe a letter. Say it looks rather V-shaped. And if we wanted to write down an equation of it, we typically do so in a piecewise function. So the absolute value of x is defined to be one thing when we are to the left of 0. It's the line minus x. And it's defined to the right of 0 to be something else. The line y equals positive x. So this is defined to be minus x when x is less than 0, and positive x when x is greater than or equal to 0. And note, this should make somewhat intuitive sense. If you substitute in a quantity which is negative, you have to take the opposite of it to make it positive. And if you substitute in a positive quantity, you just get out the same thing. So if we think about this from a differentiation perspective, our guess would be f prime of x. If we had to differentiate it, note, thinking of tangent lines, the tangent line for any point to the left of minus 1 is that line y equals minus x and has a slope of minus 1. So we would guess minus 1 when x is less than 0, and similarly positive 1 when x is greater than 0. And you can verify that using the definition of the derivative. What I want to focus in on, though, is this point that's kind of in the middle. What happens at x equals 0? And as indicated or maybe conjectured in the previous example, because of this sharp point, the derivative is defined to be one thing to the left of 0 and something else to the right of 0. It turns out that this function is not differentiable at 0. So what I would like us to explain or explore, why does f prime of 0 not exist? And the only tool we really have at our disposal is to go back to this definition of the derivative. So in terms of that definition of the derivative, we can write out f prime of 0. It would be the limit as h approaches 0 of the difference quotient, f of 0 plus h, minus f of 0 all divided by h. And note that f of 0 itself, that's equal to 0 because we have this point 0, 0 on the graph of the absolute value function. And 0 plus h is simply h. Therefore, this derivative really becomes the limit as h approaches 0 of f of h over h. And f is the absolute value function. So one more simplification, this would be the absolute value of h over h. So let's just think about this for a moment. We want to know the limit as h approaches 0 of the absolute value of h over h. Well, the absolute value function is defined to be one thing to the left of 0 and another thing to the right of 0. So if we would like to evaluate this limit, we really need to break it down into a left and a right limit. So let's consider kind of two possibilities. If we want to think about from the left, i.e. h less than 0, we would have the limit as h approaches 0 from the left of the absolute value of h over h. Well, if h is less than 0, that corresponds to a negative input. And what we get out from the absolute value function would be minus h. So that is the limit as h approaches 0 from the left of minus 1, and the limit of a constant is always that constant. And let me just note, from the left of 0, getting back this minus 1 matches up very nicely with our previous intuition. So let's think about the right-hand limit. If we take the limit as we approach 0 from the right, we're thinking our h value would be positive. So in that case, the limit as h approaches 0 of the right of the absolute value of h over h. If h is positive, the absolute value of h is itself, h. H over h is simply 1, and the limit of a constant is always that constant. And once again, note that 1 that we get matches up with our intuition previously of what we would expect to happen to the right of 0. And now we have our reason as to why this derivative does not exist. F prime of 0, if it is to exist, is the value of this limit. But when it comes to evaluating this limit, the left-hand limit and the right-hand limit do not agree with each other. So we now have our desired conclusion. So therefore, we have shown f prime of 0 does not exist. And note, to say that f prime of 0 does not exist, that is equivalent to saying f is not differentiable at x equals 0. And as we are going to conclude in a few minutes, when it comes to looking at the graph of a function and determining will it be differentiable or not differentiable, a function can fail to be differentiable for two types of reasons, which is our next topic of discussion. And it turns out that the first reason is what we've seen in our current example. This function fails to be differentiable at 0 because the graph of the function has a sharp point, or what we might call a cusp, at that value. And there's also a secondary reason as to why a function might fail to be differentiable. And it comes from the following property. And the following property tells us that if f is differentiable at x equals a, then f is continuous at x equals a. And I'd like to explore this statement a bit. I guess I was initially thinking I would maybe explain why it's true, but I think we can maybe have a better discussion in terms of its relationship to calculus by just thinking about kind of if-then statements in general. Now, when it comes to if-then statements, we do have to be, particularly careful about the order. If something, then something else. So let me ask you a question, kind of to get us going. If we reverse the order, that is mathematically if we were to discuss the converse of this statement, if f is continuous at x equals a, then f is differentiable at x equals a. And I'm not making a statement, I'm really asking a question. Is this true? And I want you to, maybe pause the video and kind of ponder on this for a moment. So what do you think? Hopefully what you're saying is, no, this is not true. And the reason being, and I'm just going to kind of reference it here as an asterisk or a star is if we go above to this example that we dealt with the absolute value, it gives a perfectly good example illustrating this. So the absolute value function is most definitely continuous at x equals 0. I can easily draw that without lifting up my writing utensil, but the absolute value function is most definitely not, at least we've just shown this, differentiable at x equals 0. So now for the good part, kind of an important property. So even though we can't directly reverse the order of an if-then statement and get back something that's true, what we can do is take what's mathematically called the contrapositive of the statement. That is, if the conclusion is false, then so is this hypothesis. So a property that we can use is if f is not continuous at x equals a, then f fails to be differentiable at x equals a. And this will be a property that we can make use of. So as I've claimed, a function can fail to be differentiable at a point for two different reasons. And we've now seen both of those reasons. The first way that a function can fail to be differentiable at a is if graphically the graph of the function has either a sharp point or a cusp at a. So this function f is not differentiable at x equals a because there is a sharp point. So a sharp point or a cusp in the graph, that would imply that f prime of a does not exist. The other way that a function can fail to be differentiable is if it's not continuous. So just a generic graph of something not continuous might be something with, what we previously had referred to as a jump discontinuity. So note, this is an example of something not continuous at x equals a. So once again, it's the other way that a derivative will not exist. And just to recap, a derivative will not exist if one of two things happens graphically. There's a sharp point or a cusp in the graph, or the function is not continuous at a point. In our next video, we'll investigate a graphical example of this, and then move on and begin discussing multiple derivatives just to foreshadow future conversations. So stay tuned and take care.